Maybe I start from another position. I've been for 18 years now a member of the math expert group in PISA, and I want to clear one thing. Namely, some people understand that mathematical literacy is applied mathematics. That means you have to have everything in real life context, otherwise it's not PISA. Now, I refer you to the definition of mathematical literacy. It starts with the words mathematical literacy is the ability to reason mathematically, and only then it comes to the different situations that you have to deal with in real life. So the method is the key, not what it deals with. Some parts of mathematics are more natural in the abstract context, some are more natural in the real life context. And this should be mixed by the teacher. So in our curriculum, we do not have parts like abstract mathematics and applied mathematics. We have description of certain mathematical abilities that you have to acquire. And then in the commentary, we add that we list some real life situations that you should be able to deal using these abilities to with those situations. So it is also not true, in my opinion, that abstract mathematics is more difficult than applied mathematics. It's not true. One example, take a Sudoku puzzle. It's pure mathematics. It's an axiomatic system. Yes, you have clear definitions what you can do, what you can't do with this puzzle. And once you explain it to a student, he behaves or she behaves mathematically, follows the rules. Yes. And furthermore, if you make the following exercise in a classroom, I encourage you to do so because I tried. It's a wonderful. When you tell the students that explain to me why you cannot put 1 in this position, but in writing, then they start writing mathematical proofs. If I put it there, then I get a contradiction with another row and so on. It's a proof by contradiction, but they invent themselves. Why? And they do it willingly because they think they play. Just a game, but that's pure mathematics. It's a completely defined object which they deal with. Is it useful? Oh, just for fun, but it's worth trying. So on the other hand, if you just stick to abstract mathematics, then you make a false assumption that every student who knows abstract mathematics can apply it when necessary. Not true. We had a very painful experience in Poland about the year 2000, when in the final exam in high school, we had 2 problems. One problem was investigate the behavior of a function given by a formula by using the first as a second derivative and the second derivative. And this was solved by about 70% of students. And a simple problem about percentages, where more than half failed. What does it mean? This abstract knowledge didn't help to solve a very practical, simple problem. This bridge between abstract and practical can be built only by the most talented students by themselves. So you must be very careful about it. But we should also remember that most of the abstract mathematics did grow up from practical situations, and we shouldn't forget that. We tend in our textbooks to write the Thay's theorem that when you have an angle and you cross its sides with 2 parallel lines, then certain segments are proportional. Okay, that's usually what you see in the textbooks. Now, how did this author of this theorem in the year -600 formulate it? If you want to measure the height of a tower, wait until your shadow is equal to your height, then measure the length of the shadow of the tower, and you know how high it is. That's the formulation, original formulation of the mathematician who invented this rule. So we should not forget that. We are talking about similar triangles as something abstract, which is useless. Now, where did that appear in the past for the first time, actually applied? That was Aristarch in the year +300, when he was considering or discussing or wondering how far it is from Earth to the moon and to the sun. They seem of similar size in the sky, but sometimes the moon comes in front of the sun, so probably it's closer, but how close it is compared to the distance to the sun? How can you do that? He said he had the knowledge of a 5th grader of today's school. Yes, so he said, if I could draw this triangle, Earth, Moon, Sun on the sand, and compare the sides, I mean a similar triangle, compare the sides, I would know the answer. How to draw a similar triangle. He knew what our students know. You must know the angles of this triangle. Our students know what he knew, that the sum of the angles is 180 degrees. So you need only 2 angles to measure. One angle is on the Earth, so you can measure it, yes? But where to get the other angle from? That's his idea. Wait until it's the right angle at the moon. Where it is so, when you see half of the moon exactly. He did that, measured, and discovered that the sun is 400 times further away from Earth than moon. Every student should know that. Then they will appreciate the similar triangles, because that was the only tool. Yes. So there's a big cultural background behind all this. If we wash out all this culture from this and leave a pure, clean theorem, you lose all that and you lose the motivation. So we should go back and dig and look for this context. Then it is fun. You should remember that learning mathematics is not only because it's useful. If we arrange classes this way, we are lost, because then you start the discussion, which fractions are useful. You never go to shop to buy 1/7 of a kilogram of meat. Yes, so possibly the fraction with the denominator 7 is not useful. So maybe we should throw it away. Stay with the fractions with the denominator 10. Yes, and so on and so on. You would destroy the whole picture. It would become just the Babylonian mathematics, which was just the cookbook. Yes, when you want to calculate this, you take this recipe. When you want to calculate that, take that recipe. It's not the modern world approach. You should defend the cultural side of mathematics. And I've been to a conference in 2016 in Switzerland when there was a lecture which with the title what is not useful in mathematics and we can remove. Would that person ever dare to tell the same about the teaching of language? Which kinds of poetry is not useful today and we can delete? I mean, it's part of our cultural heritage, mathematics. We should not forget that. It's useful, wonderfully useful, we know that. And we should show when it's possible. But of course, there's a price for that. Namely, you have to do two things which are outside mathematics. You have to build the model, then deal mathematically, and then evaluate the model after you get the result. Many teachers of mathematics think it's a waste of time. It's not a waste of time if the situations are chosen correctly. So you have to be very careful about it, because you pay with time, but you should be sure that students will not get ridiculed by someone that they are trained in mathematics but cannot deal with a very simple mathematical situation in real life. So you need really a good mixture, and a good teacher knows that. And we don't have to decide on the level of a state whether we go the way of applied mathematics or pure mathematics. This question, I think, is a nonsense question. You should forget it. Teach the method of mathematics, mathematical reasoning as a background for all this. And that is very important to understand it this way, because some people, it's very natural for a teacher who teaches for many years to realize that he is teaching some concepts, practices them, and some procedures how to deal with these concepts, because that is easy to test. But that's not mathematics. That's learning by heart. I knew a teacher who knew 30 types of problems that he would teach to his students over the high school, and then they would be successful. There's nothing worse than that. I mean, a well-trained student in mathematics does not run away from a problem he has never seen before. That's a good measure. I mean, you offer a problem, and many students say, no, it was not covered at school, so I don't have to solve it. You had bad mathematics teacher. A good mathematics teacher will say, look, it looks like you would never be able to solve it, but just think a moment. And then the kids start thinking, well, it's similar to something I know, yes? And then it progresses. There are two kinds of countries. when I look from the perspective of PISA, there are so far not so many items of this kind, but we have full tables of results. There are countries where students usually run away from problems they have never seen before, students who attack them. Not always a success, but start doing. And this is a great distinction. So a good education system trains students for surprises, because that's real life now. In real life, you cannot predict at school all situations when mathematics would ever be used. And it can be more often used than you imagine. Yeah, I finish with one anecdote because that happened to me in Warsaw. I was going with an elevator with an elderly pair, a woman and a man, and a man has a quite large stomach, and the wife between these floors says, they say that when you drink a lot of beer, you get a large stomach, but you don't drink beer. Yes, of course, I immediately realized she made a logical error. She reversed the implication. If you are trained in mathematics, you see that immediately. She didn't know that implication y way is not going both ways. Yes, that's mathematics.